Hello guys, welcome to the new video. Today we are going to see the topics which are mentioned here. First one is, wait a minute, just have to customize my screen for pen tab. That's it. Thank you so much. So let's see what are the topics. First is process to transition diagram, and second one is scheduling queue, and last topic is dispatcher. So we will see what are these three topics are, and let's first change the colors. Blue to this black to yellow, I think. Yes. So let's start with first topic, which is process versus. We see in last video what is process and program. Program is uh, statements which are stored in disk. It's a passive entity, alright. And process is program in execution, and number two thing is it's an active entity process, right? And how it is stored in memory. Yes, a program which is stored in memory is stored in memory is called process, right? Program. So yes, this is how it works. And let's see what's the next thing is. Uh, how it is stored in memory. So the code section instructions are stored in text area, and the global variables and static variables stored in data section, and the dynamic memory access, dynamic memory, dynamic data stored in heap section, dynamic memory access. This is DMA, and it can grow as data is increase, and the stack area stores uh, the function stacks, right? This is how, and the addressing start from text area to stack, from minimum memory address, max memory address, right? This is how it works. .bc initialized data stored in .bcs section, initialized data is stored in bss section. So this is also we talked in last video, right? So as we know that process is a abstract data type, all right. So it can have attributes and operations, all right. So the attributes of a process could be identification, out we identify a particular process, all right. CPU related attributes is program counter, priority of a process, state of a process, general registers, type of a process, burst time of a process, how much time it will take on CPU, all right, to execute, and memory related attributes are size of a process and limits All right. Uh, and we see in last video that every process has its product process control block, PCB, stored in memory. All right. And file related is list of files in use when we execute a process. All right. So these are all attributes of a process are stored in a table known as all attributes are stored in program control block, process control block, PCB, or we can say process descriptor, which stores description about process. All right. And each process has its own PCB ID card. All right. To identify the process. This is also the, and now we see that this is program process control block for every process. What things it can store a pointer from uh, pointer to address at memory. Right. Process key, process state, process number means ID process, ID of the process, uh, program counter, process counter or program counter. Right. Registers, memory limits, list of files. So these all are attributes are stored in uh, PCB. Right. So now we will see process states and state diagram of progresses. So there is a process state new. When a process gets created, resources are allocated to the process. Right? Resources are allocated to the process like memory, all right, IO device and CPU, uh, threads, etc. These are resources are allocated to the process, all right, not the CPU, the memory and IO devices and so on. When when a process gets created, now it will transit in ready state. Ready state run to run on CPU. So now the process is queued. Let's say this is process 1, this is process 2, and process note is executed on CPU. Now the turn is for process 1. So in the ready state, this is ready state. After that, it will run on execute on CPU. So after this, uh, ready state, running state is it will go to running state execution of instruction on CPU. Now it starts its execution on CPU. After uh, P node leaves the CPU, P1 will start executing on CPU and start executing its instructions. All right. And number four, after from running state, this is a block and wait state needs to perform ID or system calls. If while running on CPU, if some process need to perform IO or system call operations, so it will go to block and wait state. All right. And terminate state resource reallocation. That means after completion of execution, when the process completes its execution, it will terminate and reallocate or release its resources that it collected. All right. So now we will see the diagram. So, this is the diagram. Process state transition diagram. Now new is is a process is created, right? uh, uh, this is and here process is in disk, all right, in a new state and hard disk. So it get creates and it come to the ready state, all right. Here in ready state, it gets its uh, what to say, resources, all right. And after ready state, it can go to running state, all right. And while in running state, it can go to uh, IO state, means block and wait state for perform IO operations or system call operations, all right. After block and wait, it cannot directly go to running state. It will go to ready state first. Now after it gets its chance, it will go to running state. It can perform this cycle several times, and after after this can go to, after it completes its execution, it can go to terminate and release the resources. All right. Yes. So this diagram is for the, if we have a multi-program OS. All right. If we have a multi-program OS, so in this, from ready state, it can go to uh, a suspense ready. Let's say uh, it can go to, let's say that program process one needs three resources: resource one, resource two, and resource three. All right, and it can get only resource two and resource three at ready state. It cannot get resource one because it's in use with other process. So it can go from ready state to suspend ready state, and it can resume its execution after getting resource one. It's again get to ready state. All right. And in from running state, in case of multi-programming OS, it can go to suspend state. All right, it can get suspend because let's say process one is running on CPU. All right, and there is a process zero which has higher priority than process one. So it get the CPU, took over the CPU, and process one will go to suspend state. All right, and again after it's getting its chance, it will can come to ready state and again starts executing. All right. uh, in such what to we left here. Yes, block and in from block and wait state, and it also can go for suspend block and resume state. This is the same case as suspend ready case. Let's say that there is a process one, all right, which needs uh, to perform IO, all right, and there is a process two which was already performing IO operation, all right. So process two already has what to say, higher priority than process one. So process one has to wait, all right. So it can go to suspend suspend block state, and it can resume again in I directly from its here IO operation, all right. Or it can, we can say that after uh, also or after completing its IO, it can go to ready, suspense ready, because there is no resource for process one or process. Let's say process two, it completes its IO operation, all right, and it go to it. and it requires resource 1 and resource 2, but resource 1 is not available, so it can go to suspense ready state directly. All right, after getting its resource, it can come to this state. All right, now this is how it works. So I hope you understand, and you will thinking, you would have thinking that what is this dispatch. So the dispatch is, uh, we will see this, and we will see this later. All right. For this, let's see what's in this. So what does the note say? Take a note. As long as process is in ready or running or block state, it is in the main memory. All right. There can be many ready block processes. All right. As I said, told to you, there is a queue and ready state, ready queue, and there could be queue and block state process. Maximum number of running process depends on number of CPUs. Alright. If we have one CPU, only one process can run on CPU at one time. If we have two CPU, uh, only two process can execute uh, uh, simultaneously. Alright, at a time. So let's see. Process instance diagram is of uniprocess. Alright, uniprogram OS. So it has a new state. Alright, and now there is no ready state. All right, so direct it to go to running state, and it perform IO. After completing IO, it to complete, then it release the resources, then only can a new process can create it. All right, so only one process can store in memory at a time. All right, this is how it works. Only one process can uh, store in memory, multi, in uh, in uniprogram OS. All right. So what is this? Is this is a ready queue and various IO device queues. All right. So queue header tail. So in this is a, let's see, this is a ready queue. So process 7 and process 2 is in the queue right now, which is ready to execute on running on the CPU. All right, and this is memory tape. This is disk terminal. This is IO devices. All right, these are all IO devices. Uh, uh, a system can have multiple IO devices. All right, memory also considered as IO device. All right, memory means secondary memory. All right, this is also IO device. Job queue. This is or another terminology for job queue, means this is a new state. This is ready state, CPU, IO, IO waiting queue. All right. So this is the this is termination state. This is equivalent to new state, job queue. How suddenly queue works? This is a ready queue. Let's see. After ready queue, it will go to execution for CPU. It can terminate from here. Else, it can go to IO request or alright. Then IO queue, it can enter IO queue, IO, and again it can go to ready queue. Or let's see if it has a priority, or let's say it has a fixed time. Alright, fixed time of execution on CPU, fixed time slice. Alright, it only 10 ms. Alright, let's say uh, it execute for 10 ms, then it will suspend for but for a given time. Alright, then time slice expired, it will go to this, then again it will go to ready queue. Fork a child, let's say uh, there is a in process there is a fork statement. All right, so it can go, it will create a copy of that process. Right, that means duplicate of a process. So fork statement creates the duplicate, so it starts its own execution and the child execution. After, the child will go to ready queue. All right, interrupt occurs. If any interrupt occurs, so wait for an interrupt, and after execution interrupt interrupt cycle, it will again come to ready queue. All right. So there are several uh, things from which a process can suspend from CPU. All right. Let's see, job queue, LTS, MTS, STS. What are these things? Is LTS is long. Let's see, short term. I am forgetting. Let's see what is this. LDS, MTS, and STS, and STS. LES long-term schedulers. All right. MTS medium-term scheduler. Let's see what are they. Long-term scheduler is responsible for selecting process from a job pool, right? A job of new process. In bringing them into the system, the LTS determines which process should be admitted to the system for execution based on various criteria such as system load, available resources, process priority. Once selected, the process are moved to ready state where the wait for CPU timing is execute. The LTS is typically invoked less frequently, alright, compared to other schedulers. This is the key point. LTS is typically invoked less frequently. So its invocation frequency is less. Medium-term scheduler, the optional component in some software systems. Its primary function of manage the number of processes in memory. Uh, let's see, MD helps in balancing the system of overall performance by controlling the number of processes present in memory. How many process can be uh, process is known as swiping in and swiping out. Later, when the process MTS might decide to swap out some processes from the main memory to secondary storage, and it can swap in the process from secondary memory to main memory. All right. STS is short-term scheduler is known as CPU scheduler. All right. It's also known as CPU scheduler. It is a scheduler that operates most frequently. All right. decide which process that from the ready state should be allocated the CPU for execution. Alright. From ready queue. It was between ready queue and CPU execution. Alright. Make quick decision based on specific criteria and STS make quick decision based on such as process priority, burst time, quantum time, its whole CPU utilization. Alright. So let's see what does this say. LTS invokes less frequently, alright? Less medium, it invokes uh, medium. It invoke at medium frequency. STS invokes at high frequency. Alright. So STS also short-term scheduler also known as CPU scheduler. Right. Consider a system having n CPUs. Alright. And n is greater than of 1. K processes K is greater than n. So there are n CPUs. Let's say n is 2 and K processes. Let's say process 1, process 2 and process 3. Calculate lower bound and upper bound of the number of processes that can be held in block state. So, as we know, the there is a queue for ready state. So, any number of uh, states as we want can store in ready queue. All right. So, it will should be n means the number of processes ready queue could be in running state only n processes because the as the number of CPU is equal to number of process in running, right? In execution. So this is running state only and block state it could be k. The number of as many process as we can as memory can support will be in block state. All right. Or if n is greater than n and k is less than n, so all answer will be k, the number of processes, alright? Because the number of CPU is greater than number of process, alright? So it can be k. The process transition given below is representative of there is a new state, ready state. It can go from new to ready to running to back to ready. From running, it can go to block to ready. It can terminate. So it should be a multi-program OS, preemptive scheduler. All right, it can preempt while running. All right, preempt the process. Preemption is taking place here. OS with non-preemptive scheduler. No. Batch OS. OS is uniprogram. Uniprogram OS. No. The answer B is correct. All right. Let's see what's in this question. In the following process states a transition diagram for a unique processor system. Unlike only one processor. Processor is one. Assume that there are always some process in ready state. Always in ready state. Alright, infinite number of processes ready state. One, two, then so on. Now consider following statements. If a process makes a transition D in this means running to terminate. Alright. It would result in another process making transition A. Alright. It come to ready state. Alright, ready queue. Ready queue. Right. Immediately. A process P2 in block state can make transition E while another process P1 is in running state. Alright. The OS uses preemptive scheduling. The OS using non-preemptive scheduling. So what this is want to say, which of the above statements are true? So in this transition diagram, when if a process makes a transition, it will result in another process making transition immediately. It could be true, but as many processes as we want can be in ready queue before a process. There is no relation in termination and ready state. All right. So this could not be must true. It is a true that it is not a must true. A process block state can make transition E while another process P1 yes it can make transition this preemptive. I think second and third is the right option. Yes. Which combination of the following features will suffice? What is this? Which combination of the following feature will suffice to characterize an OS as a multi-program OS? So what is suffice means? We should work on our English to crack gate exam. So suffice means be enough. So how many features be enough will be enough to characterize an OS it is a multi-program OS. So what is this? More than one program may load into main memory? Yes. At the same time of for execution? Yes. If a program waits for certain events such as IO, another program is immediately scheduled for execution. It could be true, but if execution of a program terminates, another program is immediately scheduled for execution. This is not directly connected for. This is not enough. This is enough. This is the only enough condition for the multi-program OS. Alright, this only is the correct option. These are our, these are necessary conditions, but there are not enough conditions. This is the enough condition, so this is the correct option. A minimum number of processes that can be in block state for a computer system with n CPU is n with n CPU n square independent of n. Yes, ready and block are independent of n. We know already. So consider following statement about process transition for a system using preemptive scheduling. Uh, Consider following statement about process state transition for a system using preemptive scheduling. A running process can move to ready state. Ready state, yes, it can preempt. A ready state process can move to running state, yes. A block state can move to running state, no. A block state can move to ready state. Block state, yes. So first, second, and fourth are correct only. So thank you guys for this video, watching the video. I hope you like this. This is the revision classes. Thank you so much.